Okay, hello everybody. My name is Alvaro Lopez Garcia. I work at the Spanish National Research Council. And in this short presentation, I will show you how and why we have implemented this functionality for OpenStack. So this will be the outline of the presentation. First of all, I will put you a bit into the context of why we have been doing this. Then I will present the design and finally some wrap-up and conclusions. Okay. So as I said, I work for a research institution, and one of the tasks of our group is to provide support for the different user communities that are in our institute. In this context, we participate in this INDIGO-Datacloud project, which is an H2020 project approved by the European Commission last year. We are 26 European partners from 11 EU countries participating into this project, and our aim is to develop an open source platform for scientific computing and data. We are focusing on several multidisciplinary communities that are not related between them. We have collected the requirements from 11 initial communities, and we try to consolidate these requirements into user requests that we are then trying to map into our design for a platform as a service to satisfy their needs. However, in order to do so, we have found several technology gaps. For example, the existing vendor lock-ins that you already know, either at the supervisor level or the technology level, we have found an inflexible way of distribution applications. And the problem that affects us here, that we have found that the resource allocation strategies in the cloud middleware frameworks, more specifically in OpenStack, they are too simple for our needs. This prevents the users from exploiting effectively the resources when the requests are a bit more complex, and this makes resource providers also difficult to give them a good experience, leading to the underutilization of resources. So why we do consider that this is a problem? First of all, because as I said, we consider that the current scheduling is too simple. This is focused on satisfying the industry needs, and we consider that this is not feasible for us because, for example, we cannot accept idle resources, but for the industry this may not be a problem because you are getting money for those resources even if they are not being used at all. The schedulers also are too simple. There are no priorities. This forces us to do a static partitioning of the resources. The quotas are static. The queuing, if it exists, is too simplistic. So this doesn't work for us scientific providers. So this renders into two different problems. One for the resource provider, where we have difficulty to partition the resources. We have to arrive to a compromise between using the infrastructure as much as possible and give enough share to each of the groups. So it is difficult to make a good utilization of the infrastructure because we cannot do backfilling, where this backfilling was possible, for example, in traditional batch systems, and it's difficult to prioritize workloads for different users and groups. And from the user's point of view, it is difficult to exploit the resources because they can perceive that they have a limited quota even if there are free resources. Another interesting usage pattern that could be opportunistic usage. I mean, I would use as much resources as I can until the provider tells me that I'm not able to do so. This is not possible. So what we are proposing here is to introduce preemptible instances or interruptible instances instead of changing the whole provisioning model, similar to the commercial cloud offerings like Google Cloud Engine preemptible instances or the AWS Spot Market, so that we can do backfilling via opportunistic usage, so that we can implement more complex policies on top of this basic functionality, like dynamic pricing or so on. And also, we try to develop this not specifically for the scientific providers, but also for the commercial ones, because we consider that this is something useful. So we go into the design. We start with these four premises. First of all, we consider two different VM types, normal instances and preemptible ones. Preemptible instances can be terminated at any time. This is an agreement that a user has to be aware of. when they are terminated, okay, if there are not enough resources, a normal instance will be terminated if one or more preemptible instance can free up the resources for it. We try to do it as a modular design based on the weighting algorithms that already exist in Nova, so that the instance termination is completely configurable. With this in mind, we came with the following design. Now we have two different host states. One, what we call the full state, that takes into account all the VMs that are running inside a physical host, and one that we call HN, that does not take into account the preemptible instances. Filtering is based on the full host state for the preemptible ones, and in the partial state for the normal request. This will make us. This will ensure that a normal request will always get a schedule in spite of the resources being used for by the preemptible instances. Then the weighting is based for all the requests is based on the full host state, and then we introduce an additional instance selection and termination phase to select the preemptible instances that need to be terminated to give room for the normal ones. So this is the flow chart. Whenever there is an incoming request and the scheduled request is starting, we check if it is a preemptible request or not, and then we get the corresponding host state. We perform the filtering, and if there are some hosts that pass that filtering, we get the full state for those hosts. We do the traditional weighting that occurs on Nova. And then if we detect that there is an overcommit of the resources, we select the preemptible instances that need to be terminated, we terminate them, and we finally make the schedule. So the changes that we have implemented, we have developed an additional host manager that will return different host states depending on the preemptible instance or depending on the host having preemptible instances or not. We have developed a new filter scheduler that implements the functionality that I have described before. But the good thing is that with this design, we are able to do the scheduling decision into one cycle. We don't need to do an additional retry if we are not able to schedule a preemptible instance. So there is no performance penalty introduced. The scheduler remains in the same, more or less in the same, it takes the same time for scheduling a normal instance or a preemptible one. Actually, all of this is completely loadable, so no changes in the filter scheduler. This is implemented as external modules. The only changes that we need in Nova were API changes for both the public API and the private interfaces in the public API to expose this functionality so that a user is able to tag an instance as preemptible or not. And in the internal API, we need a patch to tag the instance as preemptible as well. This is an example of the weighting function that will take into account, that will weight hosts taking into account the consumption periods of 1 hour of the preemptible instance that is there. This is a normal. This is implemented as a normal scheduler weight function. And then we have evaluated this algorithm first of all to check if it selects the less costly instance for the provider, taking into account the implemented weighting functions. And then we evaluated the performance. The bar in blue is the original scheduler time for a scheduling cycle for one VM. Then the next three ones are with the preemptible scheduler. The first one only scheduling preemptible instances. The second one only scheduling normal instances. The third one is scheduling a normal instance involving the termination of one preemptible instance. And the three bars that are in greenish colors are with a retry cycle. And if you see, if we introduce a retry, we introduce a considerable penalty, but our implementation introduces a penalty that can be neglected. So some conclusions where we are. We have submitted an spec for this to Nova long time ago. There is still under discussion. To be honest, we didn't have enough time to push for it as it deserves, presenting this here in the OpenStack summits and so on, but we will try to do so. The first implementation is available in GitHub and the URL that you can see there. This has been released in the Indigo first release that is called named Midnight Blue, and is available packaged for Red Hat and Ubuntu. This is based on Liberty though. The future work that we foresee, well, first of all, is to try to get this blueprint approved, because we think that there is room for this functionality in Nova. Then another tricky part is that the quotas, because currently we are accounting this under the user's quota. So maybe if this gets merged sometimes at some point in Nova, we need to take into account that probably this could be done in a different quota. And then we also are starting to study OpenStack Congress for a proactive instance termination based on some policies defined by the provider, so that we are not only doing reactive scheduling, that is terminating instances whenever we cannot schedule them, but also doing this proactive termination whenever we may consider that we are in risk of filling completely our resources. So that's all, and thank you for your attention.